So hello everyone, my name is Corentin Penot. I'm a PhD student at the University of Southampton, investigating the corrosion performance of 316L stainless steel alloy deposited using wire and arc additive manufacturing. Okay. I don't know if that was me, but it worked. So I'm going to present an overview of my PhD project. So I will introduce what WAAM is and the project outline. I will talk about the experimental I used, go through some of the key results I obtained, and then conclude and talk a bit more about the future of my PhD project. So in the recent years, additive manufacturing has been extensively developed, mainly due to all the benefits that those manufacturing processes has to offer, which are a lower lead time compared to subtractive techniques, which are what is traditionally used. Also, the increased freedom of design that you can reach using those techniques. And of course, the save of raw material that you can achieve. This also allows on-site production for remote locations, such as offshore platforms or navigating ships that would otherwise be difficult to supply. So the wire and arc additive manufacturing short version is WAAM, also called DED Arc, since it is a direct energy deposition additive manufacturing process. So what WAAM is basically an arc welding torch that is mounted on a robot arm that you can see here on this picture. So the robot arm will follow a programmed path that is created on a computer, and you will be able to print your part layer upon layer. So the main difference between WAAM and other additive manufacturing processes that are more popular, such as powder bed fusion, for instance, is the fact that WAAM uses a wire, so it is wire-based as opposed to powder-based. So it allows to reach higher deposition rates. For instance, for metals like steel, you can reach deposition rates as high as several kilograms per hour. And also, it uses a shielding gas thanks to the welding torch. So you don't need an enclosed space to build up your part. You can do that in open air. And combining those two advantages, you can build large parts. So as you can see here on the diagram on the left-hand side, WAAM is situated here on this diagram, which means that to achieve that high deposition rates and to achieve the deposition of large parts, it costs the precision of the process. So you will have a poorer precision when you compare it to other additive manufacturing processes, especially those who are powder-based. So WAAM will really shine and is really relevant when you deposit large metallic structures. To give you an idea, a typical layer for a steel would be around 1 millimeter. So it gives you an idea of how precise this technology can be. So my PhD is focusing on 316L stainless steel, and I'm interested in the corrosion side and how it will corrode, especially in sodium chloride environments. This is part of an ongoing effort from TWI, the Welding Institute in Cambridge, and Alloy's Register to qualify this technique and head toward a certification so that we can use it in the industry with more confidence. So there have been a bit of work already, and I will be looking at the corrosion side of the material. We've chosen 316L stainless steel since it is a common corrosion-resistant alloy, so it was a good start. So a bit about the experimental. I've deposited 2 walls to extract samples from and do the testing on. I've used conventional welding wire that is described here. So it's a welding wire that is typically used to join 2 stainless steel plates using an SE-enriched stainless steel alloy. The first wall, which we call wall B1, is in the as deposited condition, and by that it means that we didn't implement any cooling between each layer of the deposit. So we reach an interpass temperature of 400 degrees Celsius. The interpass temperature is defined as the temperature of the top surface just before the next layer is deposited. And here, well, B2, we have implemented the cooling system between the layers. So it was pulsed air on the surface, and we were monitoring the temperature until it was below 70 degrees Celsius. So we have a final interpass temperature which is below 70 degrees Celsius. And I will explain a bit more as to why we did that. So samples were extracted from the two walls. We had disk samples that are visible here that we used to do some polarization, potential dynamic polarization scans on using a 3-electrode cell, which is described here. We used a graphite counter electrode and a silver chloride reference electrode, and it was done in 3.5 weight% sodium chloride solution. It was all done at room temperature and in open air. Then we have here square samples that were used to do critical pitting temperature tests. Shorter version is CPT testing. We use an Avesta cell to do the testing. So an Avesta cell is the cell you can see here, which main goal is to reduce the risk of having previous corrosion. We used a saturated calumet electrode as a reference electrode, and the counter electrode was a graphite electrode. We've done it in a 1 molar sodium chloride solution according to the G150 standard from ASTM. And we've also performed on the squared samples some pitting tests according to ASTM G48, which is a 24-hour immersion in a 6% ferric chloride solution at 25 degrees Celsius. So a bit about the microstructure, which is important when we look at the corrosion properties of a material. Here you can see the microstructure of an as deposited sample. On the left-hand side here is the microstructure for a horizontal sample, so it was taken perpendicular to the build direction. And here on the right-hand side, you can see the same sample, but this time it was taken on the vertical orientation, so which is parallel to the build direction. You can see that we have a dual phase microstructure. Here, the darker phase is delta ferrite, and the lighter gray phase is austenite. The microstructure is dendritic and strongly oriented. The dendrites are oriented vertically, which is also the direction of the thermal gradient during the deposition. We can also notice that we have a finer microstructure at the bottom of a layer. So this is a layer that you can see here, and it is coarser at the top, again due to the difference in the thermal gradients during the cooling process. It is interesting to compare that microstructure that we have against other existing microstructure to give you an idea of where we are. So comparing what we have with the wrought, we can see that it is really different. So this is the microstructure of a 316 wrought alloy, where we have aqueous grains and no delta ferrite in it. And this is here on the right-hand side, the microstructure that we would have for a conventional 316L weld. And as we can see, the microstructure we have is way closer to that of a weld than it is to that of a wrought, which it is of interest, and it emphasizes the fact that we need to qualify that material, since the microstructure here, welding is just in the end a joining technique. It is not designed to constitute the entire part that we will use, so it is important to go through that qualification stage. If we look a bit closer at the microstructure now, using SEM imaging, so here you can see again an as printed sample that has been electro-etched in a 40% sodium chloride solution. This etching is here to reveal the sigma phase that could be present in the material. And as you can see here, we have sigma phase present that is taking over the ferrite phase during the cooling stage. So we can notice presence of those inclusions. Sigma phase is a chromium and molybdenum rich phase, which will be problematic for the corrosion properties, since it can create depletion zones around it at its vicinity. And we need the chromium and the molybdenum within the matrix to assure good corrosion protection. We can also notice the presence of small oxides that are visible here, all the dots here. Those are silicium rich, and you can also find some other elements such as manganese and aluminium. This is perfectly normal. It's due to the fact that we're using a welding wire, a larger amount of silicium within the wire to act as a deoxidizer during the deposition. Those inclusions are found to be well embedded within the matrix, and after investigation, they didn't seem to be relevant or affecting the corrosion properties. Which is also interesting is the fact that we don't have any manganese sulfide inclusion within the microstructure. We couldn't find any, and they seem to be replaced by those small oxides instead. This is probably due to the high cooling gradients during the deposition, which doesn't allow time for those manganese sulfide inclusions to form. So at the beginning, I mentioned that I had two different walls, one with a higher interpass temperature of 400 degrees and the second one at 70 degrees and below. That was done after we realized that we had sigma phase within the original build. So we were trying to minimize the amount of sigma in the build by lowering the interpass temperature. The goal was to, by lowering the interpass temperature, we would have a higher cooling rate because the temperature of the substrate would be lower, and thus we would spend less time for a given point within the build in the sigma forming temperature range, and thus minimizing the amount of sigma. So here I've highlighted the sigma phase that has been revealed using the same etching as before. And we can see that we have indeed less sigma phase in the wall B1 than in the wall B2. By subtracting the background, we can still see that we have some sigma phase present in the wall B2, except those phases are way smaller than in the first wall, in wall B1, at higher interpass temperature. So playing on the interpass temperature successfully can affect the sigma content you end up in your build. Now a bit about the electrochemical testing. You can see on the right, we performed potential dynamic polarization scans on the different materials. We also used wrought alloys to serve as a baseline, since the goal of this technology is to replace parts that are currently manufactured using wrought technique, among others, but wrought is really a common and widely spread technique. So we used wrought samples to kind of situate where our material is in terms of the electrochemical properties. Here we can see we have a classic active to passive transition here, which is expected from a stainless steel. All the WAAM samples had higher pitting potentials. We can see here on the table below that we are around 0.5 volt for the pitting potential, and for the wrought samples we are below that, sitting at 0.37 in average, so counting those two here. We also performed critical pitting temperature, which is also a test used in the industry to qualify the corrosion resistance of an alloy. Here you can see the curves of the current density against time. So as the time increases, temperature increases, which is a standard critical pitting test. And at the moment we create pitting, we know the temperature, and that gives us the critical pitting temperature. Here on the table, you can see all the different temperatures that we had for wall B1, 1B2, and for the wrought. We have a 3-degree difference between wall B1 and B2, which is not significant considering that the CPT test technique is usually you have widespread results, or you can have. So a 3-degree difference, especially on a sample of this size, is not enough to say that you have a clear difference between the two. On the other hand, for the wrought, you can clearly see that it is well below the value we have for the two WAAM grades. In the literature, the CPT for wrought 316L would be between 19 and maybe 24 degrees. So it is below what we have of about 10 degrees Celsius. So we can say with confidence that we have a different behavior here. As for the pit shapes, this is a pit observed after CPT testing, and on the other image you can see pits formed during the potential dynamic polarization, and we can see that we have a selective dissolution of the austenite here, with here bits of ferrites remaining, and that has been observed using an SEM microscope. We've also performed pitting tests in 6% ferric chloride. So that was 24 hours immersion at 25 degrees Celsius. And the weight loss is calculated before and after the test. And you can see, depending on the weight loss, if you have passed the test or not. And here you can see we have high weight loss for all the materials, which sustain substantial damage, way more than what would be expected for a traditional 316L, let's say a wrought 316L, which is supposed to pass that test with minimum damage. So this is a bit in contradiction with what we have previously. When performing the potential dynamic test and the CPT test, we had higher CPT and higher pitting potential for the WAAM material when compared to a wrought material. And here we can see that we have the inverse phenomenon happening, where the WAAM material performs poorly compared to a wrought. This has been explained by the fact that in wrought 316L, what will govern the CPT that you obtain and the pitting potential is the presence of manganese sulfide that will act as early initiation sites for pitting. And as we can't find those inclusions within the WAAM material, we have a delayed pitting that is happening, and delayed compared to a wrought material. Here in the ferric chloride, it challenges the capacity of the material to maintain its passivity and to repassivate. And we can clearly see that the WAAM material is not really good at that. An answer that can be given is the fact that we have some de-alloying effects happening due to the fact that we have different phases. So here we've performed some line analysis across the ferrite and austenite interface and across the sigma and austenite interface. You can see here on this diagram here the molybdenum content in green and the chromium content in blue. And we see that we have a molybdenum depletion at the vicinity of the ferrite and the sigma, with the depletion zone being wider in the case of the sigma, which is normal, since sigma is more molybdenum rich than the ferrite. So what is happening is we have preferential attack at the ferrite and austenite interface. And that causes the austenite to dissolve preferentially, since it is depleted in molybdenum at that location due to the nearby phase. The molybdenum is well known to improve the pitting resistance of 316 alloys, especially in chloride content, chloride-rich environments, because it slows the active dissolution of the metal, of the matrix, And since we have a depletion at that point, we have a higher dissolution rate, and we are much likely to form a pit because of it. Now, we couldn't find any clear evidence of a chromium depletion zone, so it is still unclear whereas this here happens, and that would be preferential breakdown of the passive film at the boundary between the two phases. It is still to be determined, and I will again talk a bit more in the future experiments about this. Here we can see evidence of what is explained down here, where we have here preferential dissolution of the austenite matrix, where here we have the sigma phase, which remain fairly untouched. And this pit here, which is still in the early stage, you can see that it is initiating at the interface between the two phases. So in conclusion, we can see that for the WAAM material, we have techniques, standard testing that gives contradictory results. Sorry. When we look at potential dynamic or CPT, which are tests that are done in the industry, we might think that we have a more corrosion-resistant alloy when compared to a Rotor N6L, where in the end, as we've seen with pitting potential in ferric chloride, pitting tests in ferric chloride, this is really not the case. So it stresses for the need of better understanding what might happen during those standard tests to be able and maybe correct those tests to give meaningful results as opposed to misleading ones. So as for the future experiments, we'll run some X-ray photoelectron spectroscopy in the future to characterize the passive film that we have on top of each phase. The goal here will be to look at the chemical state of the film and see if we can find any weak points that might be located at the interface between the austenite and the other phases, which are sigma and ferrite. And also doing some PPT, post-potential static testing, which goal is to initiate a large quantity of pits on the material to see where those pits are initiating and see if we can consistently trigger pits, as I said, at the interface between the ferrite and the austenite, or if we might have other initiation sites within the material. And finally, we will try a new wire chemistry as for the feeding stock. So we have been using a conventional 216L welding wire so far, which results in having a large amount of ferrite in it, as well as sigma, as I showed. And this might be also a problem for the corrosion resistance. Sigma is introduced on purpose for welds because it will limit the hot cracking effect within the weld. But in our case, if it hinders the corrosion resistance, then we need to think about other chemistry that might be a bit more relevant for the corrosion resistance. So I would like to thank my supervisors, Dr. Jimmy Morton, Dr. Yukun Wang from University of Southampton, and Adrian Addison and Dr. Chinny Lu from TWI, as well as NSERC and my sponsor, Eloyd's Register Foundation. Thank you.
Thank you for a very interesting talk. The talk is open for questions. Bob?
It seems to me that this technique is essentially welding. Have you compared your results with normal welds?
Yes, I have compared the results with normal welds. The thing is, it is not exactly like welding. The main difference with welding is the fact that we are doing a lot of passes on the same build, so the heat profile, the thermal profile is completely different from that of a weld, which will have a heat sink effect that is that doesn't exist for the WAAM deposition, since you build up the tube really fast. So we have compared it, but we stopped comparing it because we thought it wasn't too.
I mean, do you see similar differences in the critical pitting temperature and such like for a weld compared to the parent plate?
Yeah, we see significant difference. The welds, I don't remember the values, but they are lower than what we have here.
Right. Okay. Thank you.
And it is difficult to find such data. Usually, you have the weld that is testing and the substrate that comes with it.
Yes, I agree with you there. There's a problem with separating the weld and the parent plate, even in ordinary.
And you have also diffusion problems.
Yep. Thank you.
Any other questions? Okay, I've got a couple. What did you use the same surface roughness for all of your tests?
They were polished to the same grade.
Okay,
yes.
so you were using there was no surface roughness effects.
No, it was a polishing down to 3 micron. So it was a fine surface finish.
Okay, and you mentioned in your future work you're going to look at the effects of ferrite and sigma.
Yeah.
How are you going to quantify that?
Sigma, I will do some periscope analysis, spectroscope analysis to measure the content. And as for the ferrite, for the sigma, I will do for the ferrite, I will do ferritoscope analysis. Mm-hmm. And the sigma is really difficult to quantify. You have techniques where you try and etch the sigma away, and weighing the samples, you can measure the sigma content. But it is really difficult to measure sigma. The way forward would be not to measure the sigma content, but rather try and eradicate it completely. So as polishing samples, looking at it, if we don't see any sigma, then that would be good. Because we want ultimately
a long, laborious process.
Yeah.
What about is there enough sigma in there to do area fraction on the surface?
In some of the samples, yes. So on the first wall, which is as deposited, yes, we could do area measurements. Yes, area fraction measurements. But on the others, so it will be B2, for example. No, it is too small for it to be relevant. And as I said, the goal is to eradicate the sigma completely. So.
Right. Okay. Yep.
I just wondered whether you did any electrochemistry on the wire, on the welding wire, and how that compared with the properties of the weld metal.
We didn't.
Good idea to do so.
Yeah, it would be.